Okay, hello again. So hopefully you've been having some fun with these Lagrange multipliers. It's a pretty fun method. I mean, the algebra, of course, is awful, as it often is, but the math itself is pretty exciting. Pretty exciting that works. Okay, so we've been dealing with Lagrange multipliers, so we've had only a single constraint. In real life, you're going to usually not just have one constraint, you're going to have many. So the topic of this video is Lagrange multipliers with multiple constraints. And I found this wonderful picture from, I don't know if anybody's seen this movie, probably not. This is, geez, I think this came out in the 90s. It's called Multiplicity. It's got Michael Keaton in it, and I think that's Andy McDowell. Michael Keaton clones himself because he's lazy, and so he has like one clone that's really smart, and he has another clone that's really athletic. But then they make a clone of the clone, and like the copy of the copy is never quite as bright as the original one, so he has like mental issues or something. I don't know. It's pretty fantastic. Um, anyways, that's what the background means if anybody cares. Okay, so if you have mo constraints, you have mo problems, right? Well, let's see about that. So typically, as I said, you're not always going to have one thing holding you back. You might have multiple constraints. You might have a constraint involving cost and labor, or maybe there's multiple cost constraints going on. Maybe there's storage constraints going on. Who knows? There could be 50 constraints or more, and in real life things can get very complicated. So if you have more than one constraint, the problem is not that bad. You just add more Lagrange multipliers. So for instance, let's start easy. Let's suppose that we have a function that we wish to maximize. We're going to call it f of xy. Again, it could depend on more than two variables. And we have, let's say, two constraints. So g of xy is equal to 0, and h of xy is also equal to 0. And again, this could be of any number of variables. These functions could be functions of any number of variables. The important thing is that they're equal to 0. So if they're not equal to 0, add or subtract something from both sides to get a 0. Oh, we're going slow again. There we go. So our new Lagrangian here is, I'm still using the same, math cal of L, and this fancy looking L to stand for my Lagrangian function. And it's still f of xy minus lambda times g of xy, which is exactly what we had before. But now we're also going to subtract, I'm using the letter mu, that's mu, the Greek letter mu, mu times h of xy. So mu is just another Lagrange multiplier. I use mu because, well, lambda is like the Greek letter for L, and mu is like the Greek letter for M, so they're just sequential. This is typically what you'd see in kind of math literature. Lambda and mu are your Lagrange multipliers. So you see that our Lagrangian here is now a function of four variables: x, y, which are our original variables, and now lambda and mu, which are these two like new variables that we've added in. So you've got this kind of crazy function, but the plan is the same. We take the gradient of this thing, and again, when I say the gradient, I mean the gradient with respect, so it'd be the vector composed of all the partials, the partial with respect to x, with respect to y, with respect to lambda, and with respect to mu. So you're going to end up with four equations and four unknowns, because you're setting the gradient equal to 0, just like we did before. So you got four equations, four unknowns, do algebra, solve it. What happens if we have n constraints? Oh boy, this is where things start getting fun. So we run out of letters very fast here, so I'm going to call each constraint g sub k. So k here runs from 1 to n. So there's g sub 1 of xy, g sub 2 of xy, and so on. All of them have to be equal to 0. And what I'm going to do to find my Lagrangian this time, it's going to be, if it ever loads, what's happening here finally. Our Lagrangian is going to be a function of x, y, and then instead of going lambda to mu and then trying to figure out all the other Greek letters after that, I'm just going to call them lambda 1, lambda 2, lambda 3, and so on all the way up to lambda n. So this is a function of, I guess, n plus 2 variables, and it's given by my objective equation, f of xy, minus, I'm going to take each of these lambdas and multiply them by my corresponding constraint functions and add them all up. So I'm going to subtract that whole thing off. So it's like, hopefully you can see this, that in the case that n is 2, we're just back up in the top case. But if n was 94, I would have 94 different things that I'm subtracting off. Okay, so that's the setup. So I claim that if we have mo constraints, it is no problem. This is a piece of cake, except that the algebra is going to be an absolute nightmare. So let's do just a relatively simple example. I mean, these things are by no means easy because the calculations are so cumbersome, but let's try to do the following. Pause the video if you'd like to try it out yourselves. Yeah, here we go. So we want to find the maximum value for some reason of this function of three variables, f of x, y, and z, and the function is given by xy plus yz. And we've got two constraints that must be satisfied. First of all, x plus 2y has to be equal to 6, and secondly, x minus 3z has to be equal to 0. And again, there's probably, this problem is just totally fabricated, but in real life, maybe these all stand for certain quantities that, I don't know. Make up your own story, I guess. Choose your own adventure here. Okay, so the Lagrangian is a function of x, y, and z, which makes sense because those are the variables that we started with, but it's also a function of mu and lambda, or lambda and mu, whichever order you want to say them in. And it's given by, again, your f of xy, so that's right here. That's f of xy, right? Without the minus sign. And then g of xy is right here. And then h of xy is right here. You'll notice the important thing here is that I've subtracted 6 from my middle function. That's because my constraint was x plus 2y equals 6. Remember, you have to have your constraints be equal to 0, so I would subtract 6 from both sides in order to get that constraint equation. So the green is my f, the red is my g, and the blue is my h. Hopefully, yeah, if you're colorblind, I'm sorry. So that's the setup, that's the Lagrangian. It is a function of 5 variables. Ooh, welcome to multivariable calculus. What do? We take the gradient. And this is hopefully pretty straightforward. You take the derivative with respect to x, then the derivative with respect to y, and then the partial with respect to z. And then the last two, when you take the derivative with respect to lambda and mu, you just get the constraint equations, right? You get x plus 2y minus 6. I actually have a minus sign in front of them, but it doesn't matter because I'm setting it equal to 0, right? I'm setting this thing right here equal to 0. Oh, why did it zoom in? It was sloppy. I'm setting this equal to 0, which means that if it's negative or not, it doesn't matter. It just means that x plus 2y minus 6 equals 0. And the same is true for this thing over here. So basically, I'm just getting my two constraint equations back again. So this is why in some other textbooks or videos you might see, people are only taking the gradient with respect to your variables, your physical variables x, y, or x, y, and z, and then you're just remembering that you also have these constraint equations that come in after the fact too. But I kind of like it all at once. I like to see all 5 of the variables playing in harmony. Okay, so we set this horrible 5-dimensional vector equal to the 5-dimensional 0 vector, which is 0, 0, 0, 0, 0, meaning just set each component equal to 0. And you can do a lot of algebra, which would be a lot of like substitution, elimination, other horrible things, or very little linear algebra. If you know anything about linear algebra, you can do this in like 2 seconds. It's fantastic. Just make a matrix and then find the inverse of that matrix, and oh, it's beautiful. It's a piece of cake. I did the latter. I did linear algebra, and I found that x had to be 3, y had to be 1.5, z had to be 1, lambda had to be 2, and mu had to be negative 0.5. Okay, you can trust me on that if you want, or work it out yourselves, but that's what I'm getting. And so remember what the question was. We wanted to find the maximum value. Well, the maximum value happens when x, y, and z are 3, 1.5, and 1, respectively. So I just plug those values back into the original function, and I'm getting 6. So the largest that this function can possibly be, subject to these two constraints, is 6. And that has some meaning for, I don't know, profit or whatever, depending on the problem. Okay, so again, this is a relatively simple example. I did not show you any of the algebra again because it's cumbersome and terrible, but definitely something to practice. Go through this yourselves and trying to convince yourselves, this all makes sense, and good luck.